we've discovered methane and carbon dioxide in the atmosphere of this Earth-like planet called K2-18b. This was James Webb Space Telescope, just continuing to drop. I love it. New stuff all the time. New investigation with NASA's James Webb Space Telescope into K2-18b, an exoplanet 8.6 times as massive as Earth. That's giant. Has revealed the presence of carbon-bearing molecules, including methane and carbon dioxide. Webb's discovery adds to recent studies suggesting that K2-18b could be a Hycean exoplanet, one that has the potential to possess a hydrogen-rich atmosphere and a water-ocean-covered surface. I find it so fascinating the way that these telescopes actually find out what kind of stuff a planet is comprised of. What they do is they focus in on the star of a solar system, and as the planet passes in front of the star, in between the telescope and the star, it registers the way the light passes through the atmosphere of the planet, and the way it changes the color gradients. They can tell what things are in that planet. It's pretty incredible. It's fascinating what they are able to do. Let's see. Here's an artist concept version of it. I mean, this thing's 8 times the size of Earth. That is just massive. 8 times Earth's gravity too. That's a good point. You imagine how strong, if there are creatures there, can you imagine how strong they would be? Wow. Send a probe now. It'll get there eventually. I mean, the crazy thing is, it's like when we go to Mars, it's not like we are heading straight at Mars. We got to go, all right, Mars is moving, we're moving. All right, we're going to send a rocket this way to then like meet up with Mars, right? So if we want to actually go to this planet, we would actually have to analyze where it's moving, where we're moving, and then have a trajectory planned that, I mean, and how long would it take? If it's, let's find out how far away it is first. Okay, it's 120 light years away. So that means light traveling 120 years to get there is going to take us thousands of years. Easy. Thousands, probably tens of thousands, probably hundreds of thousands. Like, who knows? 120 light years, for us, that's ridiculously far. Okay, just down the road. I mean, technically, in this scheme of things on the on this universe that we're in, yes, it's right down the road. But for us, might as well be 200, might as well be 1,000 light years away. You know, until we're able to figure out how to do like a wormhole that we could jump there, it's not possible. Yeah. So anyway, the first insight into the atmospheric properties of the habitable zone exoplanet came from observations from NASA's Hubble Space Telescope, which prompted further studies that have since changed our understanding of the system. K2-18b orbits the cool dwarf star K2-18 in the habitable zone and lies 120 light years from Earth in the constellation Leo. Exoplanets such as K2-18b have sizes between those of Earth and Neptune, are unlike anything in our solar system. This lack of equivalent nearby planets means that these sub-Neptunes are poorly understood, and the nature of their atmospheres is a matter of active debate among astronomers. I feel like my camera is annoying. Let me just move myself over and down a little bit. Okay, it's a little bit better. All right. Our findings underscore the importance of considering diverse habitable environments in the search for life elsewhere, explained Niku Madhusudhang, an astronomer at the University of Cambridge and lead author of the paper announcing these results. Traditionally, the search for life on exoplanets has focused primarily on smaller rocky planets, but larger Hycean worlds are significantly more conducive to atmospheric observations, probably because they're easier to see. The abundance of methane and carbon dioxide and shortage of ammonia support the hypothesis that there may be water ocean underneath the hydrogen-rich atmosphere of K2-18b. These initial we really need to name this planet. Can we just give it a name, please? Anyway, these initial Webb observations also provided a possible detection of a molecule called dimethyl sulfide, DMS. On Earth, this is only produced by life. The bulk of DMS in Earth's atmosphere is emitted from phytoplankton in marine environments. Oh shit, signs of life. I mean, that actually right there is way more, I think, way more like bigger than finding the carbon dioxide and methane. Don't you agree? The fact that we only find it on Earth produced from life, and we are able to get that, or we are able to like see it. Okay, so let's see. We got methane, carbon dioxide, methane, a lot of methane. Gassy planet. Smells like eggs. We know it smells like eggs. And then the dimethyl sulfide. That's cool. That's awesome. And look, the wavelength of light. So this is actually the readings, the amount of like light blocked. Yeah, this is exactly this what I was telling you earlier about how they get this information. Is the way that the light is blocked from the star behind it. So cool. Okay, that's just explaining that. Actually, let's read that. Spectra of okay, so it's spectrograph, near infrared spectrograph. Display an abundance of methane. Okay, it's just telling us exactly what we can see. The inference of DMS is less robust and requires further validation. Upcoming Webb observations should be able to confirm if DMS is indeed present in the atmosphere of K2-18b at significant levels. While K2-18b lies in the habitable zone, it is now known to harbor carbon-bearing molecules. This does not necessarily mean the planet can support life. The planet's large size, with a radius of 2.6 times the radius of Earth, means that the planet's interior likely contains a large mantle of high-pressure ice like Neptune, but with a thin hydrogen-rich atmosphere and an ocean surface. Haitian worlds are predicted to have oceans of water. However, it's also possible that the ocean is too hot to be habitable or be liquid. Well, that's bullshit. I mean, there's snails on our planet that live down on like the thermal vents that they have basically iron shells. Have you guys seen these things? Hold on. Iron shelled snails. Are they snails? Scaly foot gastropod. Yeah, this is them. Look at these freaking things. Look at these guys. They've got armor. They've got armor on. Volcano snails. They're called volcano snails. So freaking cool. Okay, anyway. I think that's fascinating. Okay, let's see. The planet's large size. Okay. Although this kind of planet does not exist in our solar system, sub-Neptunes are the most common type of planet known so far in the galaxy. That was from Subhajit Sakar of the Cardiff University. We have obtained the most detailed spectrum of a habitable zone sub-Neptune to date, and this allowed us to work out the molecules that exist in its atmosphere. Characterizing the atmospheres of exoplanets like K2-18b, meaning identifying their gases and physical conditions, is a very active area in astronomy. However, these planets are outshone literally by the glare of their much larger parent stars, which makes exploring exoplanet atmospheres particularly challenging. Yeah, it must be like you must need to have the exact right angle to be able to, like, when it passes, but not directly in front of it, maybe like at more of like an edge. Who knows? The team sidestepped this challenge by analyzing light from K2-18b's parent star as it passed through the exoplanet's atmosphere. K2-18b is a transitioning exoplanet, meaning we can detect a drop in brightness as it passes across the face of its host star. This is how the exoplanet was first discovered in 2015 with NASA's K2 mission. This means that during transit, a tiny fraction of starlight will pass through the exoplanet's atmosphere before reaching telescopes like Webb. The starlight passes through the exoplanet's atmosphere, leaves traces that astronomers can piece together to determine the gases of the exoplanet's atmosphere. I know I already said it earlier, but like, that's so freaking cool that we can do that. You know what I mean? Like, that is awesome. Anyway, this result was only possible because of the extended wavelength range and unprecedented sensitivity of Webb. It is an amazing telescope, which enabled robust detection of spectral features with just 2 transits. For comparison, one transit observation with Webb provided comparable precision to 8 observations with Hubble, conducted over a few years in a relatively narrow wavelength range. That's a big difference. 2 observations instead of 8, and then it's obviously way stronger. These results are the product of just 2 observations of K2-18b, with many more on the way. This means our work here is but an early demonstration of what Webb can observe in habitable zone exoplanets. The team's results were accepted for publication in the Astrophysical Journal Letters. The team now intends to conduct follow-up research with the telescope MIRI, Mid-Infrared Instrument, spectrograph, that they hope will further validate their findings and provide new insights into the environmental conditions of K2-18b. Our ultimate goal is the identification of life on a habitable planet, which would transform our understanding of our place in the universe. Our findings are a promising step towards a deeper understanding of Hycean worlds in this quest. I can't wait for the next iteration of telescopes. For example, I just posted this the other day. This is a comparison of what Hubble was able to do versus what the James Webb Space Telescope could do. Look at this. So you've got Hubble on the bottom, so you can see how bright it is. Not a lot of detail in the middle. Like you could make out a lot of things on this edge. Here, let me zoom in a little bit more. Okay, so like, see, like you could still see a lot of things on this edge, but then when you go to the Webb, like look at the detail of the middle, right? I mean, it is just significantly more detailed. Now, this is the Sombrero galaxy. This is a full galaxy, probably billions of stars, billions of solar systems. It's just fascinating to think about. Like some of the dots that you see in the sky are not stars. You know, some of them aren't stars. Some of them are just full galaxies. I always just think that's incredible. Arriba, arriba, ándale, ándale. Yeah, the Sombrero galaxy. I can't wait for the next iteration. Like, what's next? You know, there's plans. I forget what it's called, but right now we have the James Webb Space Telescope, which is pretty huge. It's floating out there, but they want to make a full solar systems sized telescope. Right. That big. Yes. So they would go outside of not the Oort cloud, inside the Oort cloud, because the Oort cloud is like how far out the Earth's or the sun's gravity. How? I mean, we do not have the technology yet, obviously, right? We are, well, I feel like we're approaching the ability to Kuiper belt. Maybe that's what I'm thinking of. So outside the Kuiper belt, yeah. That's where Pluto's at. So like there's this outer ring basically where Pluto's at. And then if you go outside of that, essentially you're removing a lot of the space junk that is in our solar system. And therefore they would have mirrors along the all outside of all of that. And they can turn them and focus them all. So instead of having the James Webb Space Telescope, which is huge, but like it's still, you know, it could fit in a warehouse, right? They pieced it together. But like imagine one of those 10 times bigger all around our entire solar system, aimed at something. We'd be able to see potentially, like, I don't know, life. It's crazy to think about. I don't know. I'm just nerding out. You'd have to have a bunch of space vehicles. Well, of course, yeah. I mean, we would have to level up to a tier 1 society, right? Isn't it tier 1 society is when we're able to start moving around our solar system, right? Hold on, wait. What is it? Tier 1 society versus tier 2. I think tier 1 is where we can colonize the solar system. Tier 1 societies are highly advanced, often characterized by the ability to perform exceedingly accurate slip-space navigation, near instantaneous interstellar communication, and man-portable application of energy manipulation, which included plasma-based weaponry. Tier 2 societies are less advanced than Tier 1, but still possess significant technological capabilities. Okay, so Tier 1 would be the most advanced? I thought it was the other way around. What you guys know what I'm talking about? There's that, like, harnessing the power of the star. That's one of the tiers. Like, once we're capable of, like, moving around the solar system, that's an advancement. And then once we're able to go interstellar, that's like the next level. I forget like how it's actually the Kardashev scale. Okay, let me look this up. That sounds right. I don't want to use Wikipedia. Come on, give me something. Nature.com. Okay, what's this? Here we go. Forecasting the progression of human civilization on the Kardashev scale through 2060 with the machine learning approach. Ooh, this is fascinating. Okay. Let's see what this machine learning approach thinks we will be at by 2060. Okay, how long is this? Holy shit, this is very long. Oh my god. I mean, it's not that bad. You guys, are you curious? Are you guys interested in this? Next, the Star Forge. Okay, I am very curious about this. Energy, let's just read the abstract. Energy has been propelling the development of human civilization for millennia. Humanity presently stands at a type 0.7276. Wow, very accurate, on the Kardashev scale, which was proposed to quantify the relationship between energy consumption and the development of civilizations. Okay, that makes sense. However, current predictions of human civilization remain underdeveloped and energy consumption models are oversimplified. Yeah, because we're using combustion. I guarantee you there's aliens somewhere going, look at these guys. They're burning stuff. They're using steam. Okay, sorry. All right, in order to improve the precision of the prediction, we use machine learning models, random forest, and autoregression integrated moving average to simulate and predict energy consumption on a global scale and the position of humanity on the Kardashev scale through 2060. The result suggests that global energy consumption is expected to reach 887 EJ in 2060, and humanity will become a type 0.7449 civilization. Did we downgrade? Oh no, we upgraded 0.02 or no, 0.018 or something. I don't know, math. Additionally, the potential energy segmentation changes before 2060, and the influence of the advent of nuclear fusion are discussed. We conclude that if energy strategies and technologies remain in the present course, it may take human civilization a millennia to become a type 1 civilization. The machine learning tool we developed significantly improves the previous projection of the Kardashev scale, which is critical in the context of civilization development. That is really sad. That is really sad. Like 0.72 to 0.74 is not that much, right? I mean, that's kind of lame. By 2060, that's that's crazy. 35 years from now? And well, now that I say 35 years, that's really not that long, is it? 35 years. 2060 is closer than it's 2025. Wow.